Hello, and welcome to this presentation, which is an introduction to probability. Here's an overview of the contents of this probability video. The various sections included in the video are shown on the left-hand side, and the approximate start times for each of the sections shown on the right-hand side. We commence with an introduction to probability. We define the terms expectation, dependent events, and independent events. That takes us to 6 minutes into the presentation. We then define the addition law of probability and the multiplication law. Takes us to 8 minutes. Then examples and exercises 1 to 5 commence at 8.5 minutes into the presentation. Tutorial questions 1 to 5 are stated, 25.5 minutes into the presentation. Then further examples and exercises 6 to 10. And further tutorial questions 6 to 12 are stated, 47 minutes into the presentation. Solutions to exercises 1 to 5 are shown commencing 48 minutes in. The probability, usually denoted by little p, of an event happening is the chance or the likelihood of the happening or of the occurrence. Values of probability lie between 0 and 1. Where 0 represents an absolute impossibility, for example, travelling from London to Birmingham at the speed of light, and 1 represents an absolute certainty, for example, all living creatures will die. The probability of an event happening usually lies between these two extreme values, and is expressed as a proper or decimal fraction, or as a percentage. And we'll be using all three expressions in the work we're going to look at. So some examples of probabilities. A length of unstrained wire has 0 expansion at 400 degrees C. The probability of that occurring is 0. If we heat a piece of wire up to 400 degrees C, it will most definitely expand. So there's no chance at all of it not expanding if it's unrestrained. Probability 0. Probability that a fair 6-sided dice will stop on a 4 upwards when it's thrown. Probability here is 1 upon 6. There are 6 sides on the dice. One side would have the number 4, so 1 upon 6 is the probability when we throw it, we will get the 4 upwards. Percentage terms, that's 16.7%. Probability that a fair coin will land with the tail upwards. Probability here is a half. On a coin we have a head and a tail, so when we throw it the chance of getting the tail upwards is 1 upon 2, or decimal 0.5, or 50%. Finally here, the probability that a length of an unrestrained steel wire has an expansion at 400 degrees C, probability there is definitely 1. If we heat an unrestrained steel wire up to 400 degrees C, it will definitely expand to some degree. So 100%. Probability can be expressed as the total number of designated or specified occurrences over the total number of trials or items. M upon N, sometimes used for symbols. If P is the probability of an event happening, and Q is the probability of the same event not happening, then the total probability is P plus Q, and of course that's equal to unity. Since there's an absolute certainty that the event either does or does not occur. So P plus Q must equal to 1, always. Okay, let's define expectation. The expectation, often given the symbol capital E, of an event happening is defined in general terms as the product of the probability P of the event happening and the number of attempts made, usually symbol N. So expectation is E equals to P times N, product of Pn. So as the probability of obtaining a 4 upwards when rolling a fair dice is 1 upon 6, then the expectation of getting a 4 upwards on 5 throws of the dice would be E equals P times N. The probability in this case is 1 upon 6. There's one side that has a 4 on the 6 sides of the dice, and we're throwing the dice 5 times. So the expectation of getting a 4 upwards would be 5 divided by 6. Expectation is sometimes termed the average occurrence of an event. Let's define dependent event, sometimes termed a without replacement event. A dependent event is one in which the probability of an event happening affects the probability of another event happening, a subsequent event. Let's take 10 bolts at random from a batch of 100 bolts for test purposes, and the probability of there being a defective bolt, P1, is to be found. Sometime later, another 10 bolts are taken at random from the 90 remaining bolts in the batch, and again the probability of defective bolt is to be determined, P2. So the value of P2 is different from P1 since the batch size has effectively altered from initially 100 when we took our first 10 to 90 when we take our second 10 bolts. That is, the probability of P2 is dependent on the probability of P1. Since 10 bolts are drawn and then another 10 bolts are drawn without replacing the first 10 bolts, the second random selection is said to be without replacement. Let's now define independent event, sometimes called a with replacement event. An independent event is one in which the probability of an event happening does not affect the probability of another event or subsequent event happening. If 10 bolts are taken at random from a batch of bolts and the probability of a defective bolt P1 is determined, and then the process is repeated after the original 10 bolts are replaced in the batch to give P2, then P1 is equal to P2. Since the 10 bolts are replaced between the draws, the second selection is said to be with replacement. Let's look at the laws of probability. The first law here is the addition law. The addition law of probability is recognized by the word or, joining the probabilities. So if PA is the probability of event A happening and PB is the probability of event B happening, the probability of event A or B happening is given by PA plus PB. Similarly, probability of events A or B or C or N happening is given by the expression probability P is equal to PA plus PB plus BC plus etc. The multiplication law of probability. The multiplication law of probability is recognized by the word and, joining the probabilities. If PA is the probability of event A happening and PB is the probability of event B happening, then the probability of event A and B happening is given by the expression PA times PB. Similarly, probability of event A and B and C up to N happening is given by probability P is equal to PA times PB times PC, etc. Example 1. For us to determine the probabilities of selecting at random A, a man, and B, a woman, from a workforce that consists of 66 men and 40 women. So part A, the probability of selecting at random a man. We'll call that probability P. So the probability in this case is the total number of men over the total of number of people in the workforce, M upon N to use our previous symbols. So P is equal to 66, the total number of men in the workforce, over the total workforce, which is 66 plus the 40 for the men and women. That's equal to 66 over 106, and cancelling down, that gives us a probability of 33 upon 53 as a proper fraction. So decimal fraction, that's 0.6226, 4 decimal places, and as a percentage, that's 62.26%. Part B. The probability of selecting at random a woman, we denote that as Q. Note that that could also be written as the probability of not selecting at random a man, another way of saying the same thing. So the probability in this case will be the total number of women over the total number of people in the workforce. M upon N again. So in this case, Q is equal to 40, total number of women in the workforce, over again the total workforce. So 40 upon 106 cancels down to give me a proper fraction of 20 upon 53 as my probability, or in decimals 0.3774 to 4 decimal places, or 37.74%. Note that the combined probability, that is P plus Q, is equal to 1, or 100%, which of course it should be, because the probability of selecting a man or a woman from the workforce is 1. We will select a man or a woman. Exercise 1 I'm going to leave with you. In this case, you've got a bag of bolts in the stores of a workshop, contains 45 M6 thread bolts and 5 M8 thread bolts. You've got to determine the probabilities of selecting at random A, 1 M6 bolt, and B, 1 M8 bolt. The answers are in the brackets here. I will leave that with you. Example 2, we've got to find the expectation, simple E, of obtaining a 2 upwards with 4 throws of a fair dice. So don't forget, expectation is the average occurrence of the event and is defined as the probability multiplied by the number of attempts, the product of Pn. So the probability little p of obtaining a 2 upwards for 1 throw of a fair dice would be 1 upon 6. So if we've got 4 attempts, 4 throws are made, then n is equal to 4. So the expectation E is simply p times n, which is in this case 1 upon 6 times 4, so that's 4 upon 6, which cancels to 2 upon 3 as a proper fraction, or as a decimal, 4 decimal places, 0.6667, or as a percentage, 66.67%. Exercise 2 I will leave with you. In a multiple choice test having 60 questions, where each question has an A, B, C and D response, what is the expected mark if answering every question with an A? I will leave that with you. The answer is 15 marks. Example 3, we're asked to calculate the probabilities of selecting at random A, the winner of an athletic sprint race in which 5 people are taking part, and B, the winning sprinter in both the first and the second races. So again, 5 people take part in each race. So part A here, since only one of the sprinters can win, the probability of selecting at random the winning sprinter is simply given by the winning sprinter over the number of sprinters. So 1 upon 5 is the probability as a proper fraction, or 0.2 as a decimal fraction with 20% probability. Part B, got to find the probability of selecting the winning sprinter in the first and the second race. So that's given by the multiplication law of probability. So in this case, P1 is 1 upon 5. There's 5 people in the race, only 1 can win. So probability of winning is 1 upon 5. And that's also the same for the second race, P2, because again, there's 5 people in the race. So applying the multiplication law of probability, PB in this case is equal to P1 multiplied by P2. So it's 1 upon 5 multiplied by 1 upon 5, which is 1 upon 25, or 0.04, or 4% chance of stating the correct winners. I will leave you with exercise 3. In this case, you've got to calculate the probabilities of selecting at random, part A here, the winner of a greyhound race in which 8 greyhounds are running. And then part B, the winning greyhound in both the first and second races if there are 10 greyhounds in the first race and there are 5 in the second race. So be aware of that. In this case you have different numbers of greyhounds in the 2 races. Answers are given. Example 4 here, a bit more detail to digest. The probability of an electrical circuit failing in service due to a high ambient temperature is 1 upon 20. Failing due to high humidity is 1 upon 25, and failing due to shock loading applied to the circuit is 1 upon 50. We've got to find the probabilities that the electrical circuit will A, fails due to high temperature and high humidity, B, fails due to high humidity or shock loading, C, will not fail because of both high temperature and shock loading, and D, will fail because of high temperature and shock loading and not fail due to high humidity. So there are 4 parts to the question here. Example 4 continued. Let little p be the probability of failure of an electrical circuit and little q be the probability of no failure of an electrical circuit. So looking at our context of high temperature, high humidity and shock loading, PT is the probability of failure due to high temperature. From the previous slide, PT is 1 upon 20. So the probability of no failure due to high temperature, QT, is 19 upon 20. pH, the probability of failure due to high humidity. From the previous slide, pH probability was 1 upon 25. The probability of no failure due to humidity, QH, is 24 upon 25. PL, the probability of failure due to shock loading, again from the previous slide, PL was 1 upon 50, and the probability of no failure due to shock loading, QL, is 49 upon 50. So part A, the probability of an electrical circuit failing due to high temperature and high humidity, so this is a multiplicational problem here. Probability PA is equal to PT multiplied by pH. The probability of failure due to high temperature is 1 upon 20 from above, and that's multiplied by the probability of failure due to high humidity, which is 1 upon 25. That gives a probability of 1 upon 500 or 0.002 or 0.2%. Example 4 continued. This is part B now. We've got to find the probability of an electrical circuit failing due to high humidity or shock loading. This is the addition law problem in probability. So PB in this case is pH plus PL. In other words, the probability due to failure of high humidity added to the probability of failure due to shock loading. So from above we can see pH is 1 upon 25. We add that to PL, which is 1 upon 50. That gives us 3 upon 50 as the probability, or 0.06 or 6% probability. Example 4 continued again. This is now part C. We're asked to find the probability that an electrical circuit will not fail due to high temperature and will not fail due to shock loading. So again, this is a multiplication problem, multiplication law of probability. So PC in this case will be QT, that's the probability of no failure due to temperature, multiplied by QL, that's the probability of not failing by shock loading. So from above, that's 19 upon 20 multiplied by 49 upon 50. That gives a probability as a proper fraction of 931 over 1000, or 0.931, or 93.1%. Notice in part C, no reference is stated to electrical circuit failing or not failing due to humidity. So this is not be considered in the calculation. There is no QH or pH in the calculation. Example 4 continued, part D here. Now we've got to find the probability that an electrical circuit will fail due to high temperature and will fail due to shock loading, but will not fail due to high humidity. So probability for part D here is PT, the probability of failure due to high temperature, multiplied by the probability of failure due to shock loading, multiplied by the probability that there will be no failure due to high humidity. So PD is equal to 1 upon 20 from above, multiplied by 1 upon 50 from above, multiplied by the 24 upon 25 from above. That gave me a ratio of 3 divided by 3,125 as a probability, or 0.96 times 10 to the minus 3, or 0.096% probability. I'll leave you with exercise 4. It's very similar to example 4 in its structure. Just the context is different. We've got a testing program here, and we've got probabilities that a particular structure will fail in tension, compression, and shear. And there are 5 parts to this question that I'll leave you with to try and solve. Answers are given in the bracket in the bottom here. Example 5. A batch of 200 resistors contain 146 within the required tolerance, 34 below the required tolerance, and the remainder are above the required tolerance. We've got to determine the probabilities that when randomly selected, a resistor and then a second resistor are both within the required tolerance values when selecting with replacement. And part B here, first drawn is below and the second drawn is above the required tolerance when the selection is without replacement. Okay, example 5 continue. I'm going to extract information from the question. So the total number of resistors given to us in the batch was 200. Number of resistors within the required tolerance is stated as 146. Number of resistors below the required tolerance is 34, and number of resistors above the required tolerance is calculated as 200, the total batch size, take away 146, take away 34 is equal to 20. 20 resistors are above the required tolerance. So part A, we've got to find the probability that both resistors drawn are within the required tolerance when selecting with replacement. So the probability of selecting a resistor within tolerance on the first draw, PA I've called that, is 146, the number of resistors that are within tolerance, divided by the batch size of 200. That simplifies to 73 upon 100. The first resistor drawn is then replaced, and the second drawn from a batch size that is still now 200. So probability of selecting a resistor gained within tolerance on the second draw is the same as it was on the first draw because we replaced the original resistor. Thus the probability of selecting a resistor within tolerance on both the first and second draw is going to be PA times PB, so that's 73 upon 100 times 73 upon 100. That gave us 5,329 divided by 10,000, or in decimals 0.5329, or 53.3%. Example 5 continued. I just repeated this information here for convenience. So part B, we've got to find the probability that the first resistor drawn is below the required tolerance and the second resistor drawn is above the required tolerance, but this time without replacement. So the probability of selecting a resistor below tolerance on the first draw, PA, is 34, the number of resistors below the required tolerance, divided by the batch size, which is 200. That cancels to a probability of 17 upon 100. The first resistor that was drawn is not replaced, so the second resistor is drawn from a batch size of 199 now. So the probability of selecting a resistor above required tolerance on the second draw, I've called that PB here, is 20. That's the number of resistors above the required tolerance over a batch size which is now 199. Thus the probability of randomly selecting a resistor below required tolerance followed by randomly selecting a resistor above the required tolerance is given by PA times PB, which is 17 upon 100 multiplied by 20 upon 199. That gives a probability of 17 divided by 995, or in decimals 0.0171, which is 1.71%. I'll leave you with exercise 5. It's very similar to the example 5 on the previous page. Notice again you've got a with replacement consideration and a without replacement consideration. The answers are given in the bracket. I'll let you have a look at some tutorial questions here on probabilities. It's called worksheet 1 here. There are 3 questions on this slide and the answers are given in the square brackets here on each of the questions. I would suggest you attempt these. They're based on the examples and the exercises on all the previous slides. And question 4 and question 5 shown on this slide, I would encourage you to attempt. Example 6. A batch of 800 screws contains 100 that are defective. A screw is drawn at random from the batch and tested, and then a second screw is drawn from the batch. We've got to determine the probability that neither of the screws is defective when drawn. A, with replacement, and B, without replacement. We've also got to find C, what is the probability of drawing 2 defective screws without replacement. So from the information in the question, the number of screws in the batch is 800. The number of defective screws, called that little n here, is 100. The probability of drawing a satisfactory screw, P, is 700 over 800, or 7 upon 8. And the probability of drawing a defective screw, called that Q, is 1 take away the 7 upon 8, or 1 upon 8. Okay, example 6 continued. I just repeated the information below for convenience. This is part B. We've got to find the probability of selecting 2 satisfactory screws, but this time without replacement. So the probability that the first screw drawn is satisfactory from above, so probability here, P1 is 7 upon 8. Now there are only 699 satisfactory screws left in the batch, and the batch size is now 799 because we've removed one, we've not replaced it. So the probability of drawing a satisfactory screw on the second draw, P2 dash I've called that here, is 699, the number of satisfactory screws left in the batch, over 799, the batch size. So the probability that the first and the second screw drawn are satisfactory, and the multiplication law of probability, that will be P1 times P2 dash here, so it's 7 upon 8 multiplied by 699 divided by 799. That gives us a probability of 4,893 divided by 6,392, or in decimals 0.7655. As a percentage, probability is 76.55%. Example 6 continued. I just repeated the information below for convenience. So part C. We're asked to now find the probability of selecting 2 defective screws without replacement. So the probability that 1 screw drawn is defective, I call that Q1 here, is 1 upon 8. And we get that from the information in the question. Now there's only 99 defective screws left in the batch. There originally were 100 effective screws given in the question. We've withdrawn one, so now we've got 99 left. And of course the batch size is reduced also from the original 800 screws to 799. So the probability of drawing a defective screw on the second draw, Q2, is 99 over 799. This gives the probability that the first and the second screw drawn are defective as Q1 times Q2 from the multiplication law of probability. So in this case that's 1 upon 8 multiplied by 99 upon 799. That gives a probability of 99 divided by 6,392, or in decimals 0.0155 or 1.55%. I will leave you with exercise 6 to attempt. It's based on example 6 and you've got 3 parts again. You've got to look at a draw with replacement, a draw without replacement, and then a part C. I'll let you look at those. The answers are given here. Example 7. A batch of 200 components has a defective rate of 1 in 20. If a component is drawn at random from the batch and tested, then a second component is drawn at random. Calculate the probability of having one defective component both with and without replacement. So letting P is equal to the probability of drawing a defective component, and Q is the probability of drawing a satisfactory component. Given the defective rate of 1 in 20, then the probability of a defective component P is 1 divided by 20. That means the probability of a satisfactory component Q is 1 take away the 1 divided by 20, or 19 divided by 20. So in a batch of 200 components, there are 200 times 1 divided by 20. In other words, there are 10 defective components. That means in a batch of 200, there are 190 satisfactory components. Probability of having one defective component can be achieved in 2 ways. Firstly, by drawing a satisfactory component and then a defective component. So using our notation, that would be Q times P plus P times Q. Or, second way, by drawing a defective and then a satisfactory component. So that would be P times Q plus Q times P. Example 7 continued. Part A is with replacement. We're given from the question on the previous slide the probability P of having a defective component drawn is 1 upon 20. The probability Q of drawing a non-defective component or a satisfactory component is 19 upon 20. So the probability of having one defective component in our 2 draws is given by P times Q plus Q times P. In other words, we could draw a defective component on the first draw and a satisfactory component on the second draw, or we could draw a satisfactory component on the first draw and a defective component on the second draw. Notice in each case it's always out of 20 because this is with replacement. Doing the numbers on this, we get 19 upon 50 as a probability, or 0.38 or 38%. Part B is without replacement. So now for our first draw P1, the probability of drawing a defective component is 1 upon 20, and Q1, the probability of drawing a non-defective component, first of all, is 19 upon 20. However, because this is Without replacement, the probability of drawing a defective component P2 on the second draw is 10 upon 199. The batch size has reduced from 200 down to 199. And the probability Q2 of drawing a satisfactory component on the second draw is 190 divided by 199. So our probability now is given by P1 times Q2 plus Q1 times P2. So that's 1 upon 20 is the probability of a defective item on the first draw, multiplied by the 190 divided by 199, which is the probability of drawing a satisfactory item on the second draw. Added to that, we've got the situation on the first draw, we draw a satisfactory item, so the probability is 19 upon 20, and on the second draw we draw a defective item, so that's 10 upon 199. Doing the numbers on this, we get 19 upon 199, or 0.095, 9.5%. Exercise 7 here is based on example 7. I'll let you look at that in your own time. Again, we've got the with and without replacement situations. Answers are given in brackets. Example 8. A workshop storage bin contains a batch of the same size rivets, but made from different metals. There are 37 aluminium alloy rivets, 43 steel rivets, and 20 brass rivets. If 3 rivets are drawn at random from the bin without replacement, find the probability that all 3 rivets are made from brass. So from the question, we're going to assume a rivet is drawn at random, then a second, then a third rivet. The total number of rivets in the storage bin is calculated as 37 plus 43 plus 20 equals 100. Adding all the rivets up for the 3 different types of material, we get 100. The probability of randomly selecting a brass rivet on the first draw, P1, is 20, the number of brass rivets in the bin, divided by 100, the total number of rivets in the bin. That cancels to 1 upon 5. Now there are 19 brass rivets left in a batch of 99. So the probability of randomly selecting a brass rivet on the second draw, P2, is 19 divided by 99. There are now 18 brass rivets remaining in a batch of 98. So the probability of randomly selecting a brass rivet on the third draw, P3, is now 18 divided by 98, cancels to 9 upon 49. So finally, the probability of selecting a brass rivet on the first, the second and the third draw is given by P1 times P2 times P3. So putting the numbers in, it's 1 upon 5 multiplied by 19 divided by 99 multiplied by 9 divided by 49. That gives a probability of 19 divided by 2,695, or decimal 0.0071, or 0.71%. Exercise 8 is based on example 8. Again, be careful, it says without replacement here, so you must apply that principle. Answer given on the sheet. Example 9. For the storage bin, stated in example 8, determine the probability that there are no steel rivets drawn when 3 rivets are drawn at random from the bin without replacement. So the probability of drawing a steel rivet on the first draw, P1, is 43, the number of steel rivets, divided by 100, the number of rivets in the storage bin. That gives me 0.43 using decimal probability here. So the probability of not drawing a steel rivet on the first draw will be one takeaway P1. So Q1 is one takeaway the 0.43. So 0.57 probability that you will not draw a steel rivet on the first draw. Now there are 99 rivets in the batch, of which 99 take away the 43 steel rivets there, 56 are not steel rivets. So the probability of not drawing a steel rivet on the second draw, Q2 here, is 56 divided by 99. There's 99 in the batch now. The probability of not drawing a steel rivet on the third draw, Q3, is 55. 55 is the number of rivets that are not steel rivets, divided by 98, the number of rivets in the batch. So the probability of not drawing a steel rivet on the first and second and third draws is given by Q1 times Q2 times Q3. Using our probabilities above, that's 0.57 multiplied by 56 divided by 99 multiplied by 55 divided by 98. That gives an answer of 19 divided by 105 for the probability, or in decimals 0.181, which is 18.1%. I'll leave you with exercise 9 here, which is based on example 9, and exercise 9 does actually refer to exercise 8 for information. Again, we've got a without replacement situation. Answer given in the bracket. Okay, example 10 actually refers to example 8 we've reviewed previously. So I've repeated example 8 purely for convenience here to save you flipping back to try and find where it is in the video. So just for reference, in example 8 we had a workshop bin that contains a batch of the same size rivets, but they're made from different materials. And there were 37 aluminium alloy rivets, 43 steel rivets, and 20 brass rivets. So you need to be aware of that information as we now review example 10 on the next slide. Example 10. Again, for the storage bin of rivets in example 8 above, we're going to find the probability that there are 2 brass rivets and either a steel or an aluminium alloy rivet when 3 are drawn at random without replacement. So we're going to use a tabular approach here to help us look at the various configurations we need to review to answer this problem. So in the table below, we've got brass rivets are labelled as A, steel rivets labelled as B. So we're talking 2 brass rivets. So in the 3 draws, we could have a brass rivet on the first draw, brass rivet on the second, and then a steel on the third. Or we could have brass rivet on the first, steel on the second, brass on the third. Or we can have the steel rivet on the first, the brass on the second, the brass on the third. Those are our various options for drawing 2 brass rivets and 1 steel rivet. Okay, example 10 continued here. Now we're going to consider drawing 2 brass rivets and 1 aluminium alloy rivet. Again, I've denoted the brass rivets as A in the table below and the aluminium alloy rivet as C. So on the first draw we could draw a brass rivet, second could be a brass, and the third could be an aluminium alloy rivet. Or we could get the brass on the first draw, aluminium alloy rivet on the second draw, and brass on the third. Or we could draw an aluminium alloy rivet on the first draw, and then brass on the second, brass on the third. Now we've got 6 different ways that we can satisfy the question that's been posed to us. Example 10 continued. The table below is just an amalgamation of the 2 previous tables and the various configurations we reviewed. Don't forget that A in our table represents a brass rivet, B a steel rivet, and C an aluminium alloy rivet. So what we've got here are the various configurations for our first draw, second draw, and third draw. And we're going to now work out the probabilities of each of these configurations. So looking at row 1 here, we're drawing a brass rivet first of all, so that's probability of 20 upon 100 for the first draw. We multiply that by drawing another brass rivet, which is 19 upon 99 now, because don't forget there's no replacement here, so the size of the batch has gone down by 1. And then we multiply that by a steel rivet, and there's 43 of them, and that'll be upon 98 rivets. That gives us the probability of 0.01684. For the second row now, we're drawing a brass rivet to begin with, so that's 20 upon 100 for our full batch. And then we're drawing a steel rivet, so that's times by 43 upon 99. And then for the third draw, another brass rivet, so that's times by 19 of them, divided by 98 in the batch. That gives us the same value. Looking at our third row, we're drawing the steel rivet first of all, so 43 upon 100, multiplied by, for our second draw, we're drawing a brass, so that's 20 upon 99, and then third draw is 19 for the brass rivet upon 98 for the population there. Again, we get the same probability. So there's the first 3 rows of our table considered. Now we're going to look at drawing a brass and the aluminium alloy rivet. So drawing a brass, first of all, it's 20 upon 100, and that's multiplied by second draw of 19 upon 99 for our second brass, and then the one aluminium alloy rivet, there's 37 of those, so it's 37 upon 98. That gives a probability of 0.01449. Fifth row here, we're drawing a brass rivet first of all, so that's 20 upon 100, then an aluminium alloy rivet, so that's 37 upon 99, and then we're drawing another brass rivet, so that's 19 upon 98. Gives us our probability. And our final row, we're drawing first of all the aluminium alloy rivet, so at 37 upon 100, that's multiplied by a brass rivet, 20 upon 99, and that's multiplied by another brass rivet, 19 upon 98. Gives us a probability again. So if we now calculate the total probabilities, so basically in this table, probability is 3 times the 0.01684 plus 3 times the 0.01449. We get a probability of 0.09399, or rounding up, 9.4%. So to draw 2 brass rivets and 1 steel rivet, or 2 brass rivets and 1 aluminium alloy rivet, the probability would be 9.4%. I'm going to leave you with some further questions now on probability. This is called worksheet 2 here. So we've got a question 6 and a question 7. Don't forget the answers are given in the square brackets. Further questions again, question 8 and question 9 here. Question 10, question 11 here. And finally question 12, all based on the work we've overviewed in this presentation. And here are solutions to some of the exercises mentioned in the previous slides. Solutions to exercise 1, solution to exercise 2, solution to exercise 3, solution to exercise 4, solution to exercise 4 continued here, solution to exercise 5, solution to exercise 5 continued, solution to exercise 5 continued, Reference source used here to develop this presentation. I would strongly encourage you to review this book, excellent book written for technician engineers, to give you further background reading on probability. And that ends the presentation. I hope it's been of use to you. Thank you for viewing.